So welcome to our first lecture in chapter 4. We're going to be looking at graphing all of the circular functions, which are the trig functions when transposed onto a circle. In 4.1, we're going to look at the first two functions, sine and cosine. We're going to learn about periodic functions, the sine function graph, the cosine graph, how to graph, especially when the amplitude and period change, and then also connecting graphs with the equation, kind of working in reverse and looking at a trig model. So the first thing we need to learn about are periodic functions. Many things in life repeat with a predictable pattern, such as the weather, tides, and hours of daylight. This periodic graph represents a normal heartbeat that repeats at the same interval of time. If you think about the face of a clock with the hours marked 1 through 12, you know that that clock goes through that periodic function of going all the way around the clock in 12 hours. So in a single day, it actually goes around twice. And so that's the idea of a periodic function, that something repeats itself in a specific and set and consistent period of time. So here we say a periodic function is a function such that f of x equals f of x plus n times p. N is any integer, 1, 0, 1, 2, 3, etc., times p, which is that period. So what we're saying here is if we think about the face of a clock and the period is 12 hours, then we know that at f of 1, it's pointing at the number 1, the hour hand. And then if we wait 12 hours later, it's going to be pointing at 1 again. If we wait 24 hours later, or 1 plus 2 times 12, we're going to get back to that 1 again. And so 3 times 12, you know, this is, again, the third revolution, etc. So this is just a way of saying, identifying that f of x is a periodic function, because that f of x value is the same as when it repeats in that period. Okay. The circumference of the unit circle, as we go one revolution around the unit circle, it's 2 pi. So the least possible value of p for which sine and cosine repeat is 2 pi. Okay. Therefore, the sine and cosine functions are periodic functions with a period of 2 pi, and the following statements are true for every integer n. And this is just saying that the sine of x is equal to the sine of x plus any number 0, 1, 2, 3, etc. times 2 pi. So if x is, let's just say 30 degrees, or pi over 6 radians, and we add 2 pi to it, we're back in that same spot, and the sine value is going to be the same on the unit circle. And this works the same for cosine. And as we look at it, I think it's easier to see here. So what we're saying here, as we go around the unit circle, if we're at the 0 angle here, we can see that sine is 0 and cosine is 1. If we go around 2 pi units, its period, then we're going to get back to that same point or same values for sine and cosine. This is just illustrating what happens when we go around the circle. Remember, sine is equal to the y value, so let's look at that. So sine from 0 to pi over 2 goes from 0 to 1. It increases from 0 to 1. Now we're at 1, and as we go down to pi, the sine value, the y value, decreases from 1 to 0, and that's what this is saying. As we go from pi to 3 pi over 2, or a pi and a half, we go from 0 for sine to negative 1, so we're still decreasing. We're decreasing to negative 1. And then the final quadrant, as we go from a pi and a half to 2 pi, the sine value goes from negative 1 back to 0, and we can see that we've got a periodic. And you can kind of trace the same kind of concept for the cosine function. Here we see it in a little bit different fashion. We see all the values of sine and cosine from 0 to 2 pi. We see the reference angles in the first quadrant, and then we just see the quadrantals here. What we're going to do is focus on the quadrantal measures, because those are either the maximums or where they cross the x-axis. So for sine, an x-intercept is at the origin, and then we have a maximum at 1. We cross the x-axis again at pi, and then our minimum is -1 at pi½ and then we're back to 0. And so these are easy values for us to remember, and this is what we're going to use to graph different functions of sine when we're not just graphing sine x, okay, when we're changing things around that, okay. And so you can see it here. If you put it in your calculator, you would see the same thing, okay. So for the sine function, it's continuous over all values of x. It's not, there's no places where it's undefined. Its x-intercepts are of the form n pi. This means where it is an integer, when we go when you're graphing the sine function at pi or 2 pi or 3 pi or 4 pi, these are x-intercepts, or the y value equals 0. This is where it will cross the x-axis. Its period is 2 pi, we know that. And the graph, because it goes through the origin, is symmetrical with respect to the origin, so this is an odd function. And what that means is if we plug in a negative x into our argument, this will be the same value as the negative of the sine of positive x, okay? These are reflected across the origin. For cosine, we have the similar kind of graph here where we've graphed all of the values, the reference angles we know from the different triangles, and then the bottom is the quadrantals. When we're graphing cosine, we're also going to focus on the quadrantals. Again, because these are the maximums or the x-intercepts, and so those are easier values to find, and then because it's periodic, we can just keep repeating that pattern. For cosine, the graph is also continuous. Here, notice we've got some kind of weird multiplier here. We know that the x-intercept, or where the cosine is 0, is at 90 or pi over 2, and every time that we have an odd integer, so at pi over 2, cosine is 0. Well, if we add another pi over 2 to this, we'd get 2 pi over 2, or just pi, and it's not 0 there. That's at 180. It's actually 1 there. So what this multiplier in front, 2n plus 1, is doing is it's making sure that this x-intercept is always multiplied by an odd number. For example, if n is equal to 0, then we get 1 pi over 2, or 90, where cosine is 0. If n equals 1, we get 2 times 1, which is 2, plus 1, which is 3 pi over 2, which is the same as 270, where cosine is again 0. And so this multiplier, while it looks kind of strange, this is just saying that the x-intercepts are in the odd multiples of pi over 2, 1, 3, 5, etc. Its period is also 2 pi, and this graph is symmetric with respect to the y-axis, and you can see that in the graph that we looked at before, and this makes it an even function. And here, what this means is that the cosine of negative x is equal to the cosine of positive x. They're going to be reflected directly across the y-axis. Okay? All right, so let's make this a little more complicated. Let's look at the graph of y equals sine x and compare it to the graph of y equals 2 sine x. For any given value of x, the value of y is twice what it be for y equals sine x. Okay? So for any value of x here, the graph of this is going to be twice whatever that sine x value is. So the only change in the graph is the range. The y values increase. And so, again, what we see here is whenever we have whatever the value is for sine x, the value for y equals 2 sine x is just going to double. 2 times 0 is 0, 2 times 1 is 2. Notice we're using the quadrantals because these are the easiest to graph, and it's a repeating pattern, so it's quite good to do that. Double -1 is -2. Okay, here we can actually see the graph. So what happens is it kind of stretches it vertically. Okay, we still have the same x-intercepts, but now instead of our maximum at 1 and minimum at -1, we have a maximum at 2 and a minimum at -2. So this is called the amplitude. The amplitude of a periodic function is half the difference between the maximum and minimum values. It describes the height of the graph both above and below a horizontal line passing through the middle. The graph of y equals a sine x or y equals a cosine x with a not equaling 0 will have the same shape as the graph of y sine x or y cosine x respectively, except with the range, the opposite value of a and a. And so all this is saying is if we put a multiplier in front of sine x, this changes our amplitude from 1 to whatever that multiplier is, okay? The amplitude is going to be whatever that multiplier is, although the graph will go above and below the horizontal line, that value. So no matter what the value of the amplitude, the periods of y equals a sine x and y equals a cosine x, they're still going to be 2 pi. All right? So let's see what happens when we put the multiplier inside the argument. Not 2 sine x, but the sine of 2x. Well, if we look at those values, if we have x equals 0, pi over 4, all the way up to pi, and then all the way up to 2 pi, dividing them into quarters, we can see that what's happening here is we've actually shrunk our period from 2 pi to 1 pi. We can see that it repeats after just halfway around the unit circle, okay? So one complete cycle occurs in pi units. So we have a new period now. Let's look at the same thing for y equals sine 4x. So if we do those same values, notice now what happens is we complete a cycle in pi over 2 units. So our new period is pi over 2. In general, the graph of the function of y equals sine bx, this is a multiplier on the argument, or y equals cosine bx, for b greater than 0, this will have a period different from 2 pi as long as b is not equal to 1. Okay? So the multiplier inside changes the period. Remember, the multiplier in front changed the amplitude. So how do we do this? Well, what you want to do is you want to divide the interval. Now this is the new period, 2 pi over b. You might not have noticed that before, but when the multiplier was 2, we got a period of just pi. When the multiplier was 4, when b was 4, we got a period of pi over 2. So we want to look at the interval from 0 to whatever this new endpoint is, which is 2 pi over b. This is the new period. And then divide this into 4 equal parts to obtain the values for sine bx or cosine that are equal to -1, 0, or 1. This sounds really complicated, but if you build a table, it's pretty simple. So what we're going to do is, again, and I've already talked about this several times, we're just going to use those minimum, maximum points, and the x-intercepts to make graphing of sine and cosine really simple. So the first thing we want to do is find the new period, divide 2 pi by b, that's the multiplier in front of the argument x, and then multiply by 1/4 to find the new quadrantals of the function, or the distance apart. What you can do is you can multiply by 1/4 to find the first quadrantal, 1/2 to find the middle, and then 3/4 to find the last quadrantal, and then you have the endpoints, which are 0 and 2 pi over b. So let's look at an example to help you with this, okay? So we're going to graph y equals 2 sine of 2x, and compare this with y equals sine of x, all right? So the coefficient of x is 2, so b equals 2, and the new period is 2 pi over 2. This is an important formula. The period over b gives us our new period. So we get a period of 1. The graph will complete, the graph of sine 2x will complete one period over the interval between 0 and pi. So now we want to find those quadrantal values between 0 and pi. And remember, we can multiply this difference, which is pi, by 1/4, 1/2, and 3/4 to find those 3 points. okay? We're multiplying the distance between them. It's interesting that they add. I would have said pi minus 0, but it's the same value. Times it by 1/4, 1/2, and 3/4 to get those values. So here we have the left endpoint, the final endpoint, and then we have the first quarter point, the midpoint, and the third quarter point, which these are kind of thinking of as our new quadrantals. This is the very first one, the 0 or the origin, and then of course when we're back in our period. And so we can see here that what's happening is it's moving quicker. It's moving quicker. You see the blue one, this has a periodic of half of what the red function, the normal sine x. And so our frequency is increasing, and we'll get into frequency later on in the course. So for b is greater than 0, sine equals bx, will resemble the function of y equals sine x, but with a period of 2 pi over b. Okay? For b is greater than 0, this is the same with cosine. The period will be 2 pi over b. So let's graph cosine 2/3 x over 1 period. We're going to do the same thing. We're first going to find the period, which is 2 pi divided by 2/3. Remember, when you divide by a fraction, it's the same as multiplying by its reciprocal. And so here we get a period of 3 pi. Okay? So this is actually extending the period. It's making the period longer. Okay? The endpoints are 0 and 3 pi. And then the three quadrantal midpoints are 1/4 times 3 pi, 1/2 times 3 pi, and 3/4 times 3 pi, and you get these three midpoints. So here's what I was talking about, building a table. So find those, your new period, 3 pi, then find those 1/4 point, 1/2 point, and 3/4 points of this distance. Notice that when you then plug the b multiplier back in, you get the values of the quadrantals: 0, 90, 180, 270, and 360, or 0, pi over 2, pi, 3 pi over 2, and 2 pi. Well, we know what these values are. They're 1, 0, -1, 0, 1. So using a table, I think, is much more helpful than just doing it like the two previous examples we've done. Okay? So what we're going to do is, when x is 0, we're going to put a 1. When x is 3 pi over 4, we're going to make y 0. When 3 pi over 2, -1, 9 pi over 4, 0, etc. The amplitude is still 1 because there's no multiplier here in front of cosine, and so we get this function. Okay? So by building the table, again, your x values are the endpoints are the new period from 0 to the final part of the new period, in this case 3 pi, and then the other x values are those values of 1/4, 1/2, and 3/4 of that period. And then we can just plug in the quadrantals that we know. Now what happens if we have multipliers outside and inside? This is where the table can really help. Okay? We're going to follow those same steps. We're going to first find the period by dividing 2 pi by b. We're going to divide that new period interval into 4 equal parts, remember, by multiplying that new period by 1/4, 1/2, and 3/4. That gives us 4 equal parts. We're going to evaluate that function for each of those 5 values, the endpoints and those 3 points we came up with. Remember, all of these points will be either 1, 0, or -1. Okay? And then we're going to plot those points and join them with a curve having amplitude A. Really, what we're going to do in step 4 is then multiply those values by whatever that multiplier is in front, the amplitude. So if it's 2, then we're going to, if you do it in the table, then that last line and last row in that table will be multiplying by whatever that multiplier is in front of the word sine or cosine, which is, of course, the amplitude. And then we'll just draw the graph over any additional periods. So let's look at an example. We'll build this with a table, so it hopefully will be a little bit easier to see. And of course, we don't want to make it easy, so here we have a multiplier of -2. Not only does this, remember when we have a negative multiplier, It does increase the amplitude from 1 to 2, but it also flips it across the axis here. And so we'll see that as well. We'll see that as well. Across the y-axis. No, across x, excuse me. So step 1, let's find the period. Here our b is equal to 3. Our amplitude multiplier is equal to -2. So first we need to divide 2 pi by the period multiplier, which is 3. So we get 2 pi over 3. So our new period for this function is only 2/3 pi. We now need to divide this into four sections by adding, again, multiplying the distance from 0 to 2 pi over 3 by 1/4, 1/2, and 3/4, right? Multiply by 1/4. 1/4 times 2/3 gives me pi over 6. 2/3 multiplied by 1/2 gives me pi over 3. 2 pi over 3 multiplied by 3/4 gives me pi over 2 and simplified. So these are our x values that we're going to put in the first row of the chart. We're then going to go back and multiply. We're going to show what the b multiplier is. And here we get right back to the quadrantals of a normal unit circle. We know what the values of sine are for these values. So we get 0, 1, 0, -1, and 0. So we just plug that in. And then the last row is that multiplier, that amplitude multiplier, -2. So we just simply multiply each of those values by that amplitude. 0 times -2 is 0. 1 times -2, -2, 0. Oh, look, this is wrong. In my table, this here is wrong. Pay social attention. -1 times -2 should be +2. This table value is wrong, okay? So that should be +2, and then the last one, of course, is 0 again. I didn't catch that when I was building this, so apologize for that. So here, under pi over 2, we should have a +2, all right? So we're going to plot those points, and there it's correct there, pi over 2, 2. We're just going to plot those points and then join them with a curve. So we see at 0, it's 0. At pi over 6, it's -2. At pi over 3, it's 0. At pi over 2, it's 2. And then back at 2 pi over 3. And this is exactly what we'd expect. 0, again, we're flipped across the x-axis. A normal sine curve would go up and then down, okay? But because that multiplier was negative, we went the other direction. All right. And of course, we get a little note here. When a is negative, the graph of y equals a sine bx is the reflection across the x-axis, okay? We just saw that. All right, let's try another. Graphing y equals a cosine bx for b that is a multiple of pi. So here we have pi x. So it's not 3x, but it's still a multiplier. So we're going to, don't let that confuse you. We're going to do the exact same thing that we've done all along. Okay, the first thing we do is find the period, right? This is 2 pi over b, or 2 pi over pi, and so our period is now 2. The next thing we're going to do is figure out those 4 intervals, right? Finding those 3 midpoints by multiplying the period, which is 2, by 1/4, 1/2, and 3/4. And we get these values. This is 1/2 times 2, 1/4 times 1/2. Let me slow down, I'm sorry. 1/2 times 2. 1/4 times our period. 1/4 times 2 is 1/2. 1/2 times our period of 2 is 1. 3/4 times our period of 2 is 3/2. And so we get those 3 middle points that are going to correspond to our quadrantals. Now we make our table of those x values. And we can see that when we multiply it back by b, which is pi, we get back to the normal quadrantals. So we know all these cosine values here, 1, 0, -1, 0, and 1. And then the last row of the table is multiplying by the amplifier, the amplitude multiplier. And we get -3 for that. So we just multiply all these by -3. Okay. Notice our period, we're going to plot these on the x-axis, and then this will be our y value. and so we can see it here. So it's no longer over 2 pi, now it's just over 2. Okay? So these are relatively simple. It may have been confusing. We went through that a little bit fast, but if you just build the table, first figure out your period, your new period, divide that into fourths, find those midpoints by multiplying by 1/4, 1/2, and 3/4, and then build that table first with those as your x values, and then you can put the second row of the table as b times those values, which gets us back to the quadrantals. Then use your sine or cosine function, and then the last row of the table again is your amplitude. As we just saw, when b is an integer multiple of pi, now the x-intercepts and the parts that we're graphing on the for sine or cosine are now rational numbers. Like in the last one we saw 1, 1/2, 2. No, we didn't. What did we see? It was over 2. So it was 0, 1/2, 1, 3/2, and 2. Okay? What if we want to go the opposite direction? What if we want to look at a graph and figure out an equation? Well, we're going to look for two things, right? We're going to try to figure out what is the value of A, what is the new amplitude, and what is the value of B. How did the period adjust? How did the period adjust? Okay, so we can see that this graph, the graph is that of a cosine function that is reflected across the x-axis. So that tells us immediately that what we have here is a negative amplitude multiplier. Remember, if the amplitude is negative, it flips across x. So we know that A is going to be a negative number. Okay? We also know that the amplitude here is half the distance from the maximum to the minimum, and in this case, we can see that it is 2. So our A value that we're going to use for the function is going to be -2. The next thing we need to do is figure out the period. Well, we can see here that it repeats. It gets back to this same point of -2 when we hit 4 pi. So the new period is 4 pi. Well, remember the new period equals 2 pi over b. So we set up that equation, and then we solve for b. So if we multiply both sides by b and then divide both sides by 4 pi, we get that b equals 1/2. With that value of A equaling -2 and that value of B equaling 1/2, we can easily see that the equation is now -2 cosine of 1/2 x. The amplitude is -2. The amplitude is 2, excuse me. Because it flipped across the x, it's -2. And we saw that the period, the new period is 4 pi, and we calculated B by plugging it into our 2 pi over B formula for the new period. Okay? All right. The average temperature in Fahrenheit at Mould Bay, Canada can be approximated by this function. F of x equals 34 sine pi over 6 times the quantity of x minus 4.3, where x is the month and x equals 1 corresponds to January and x equals 2 corresponds to February, and so on. Okay? To observe the graph over a 2-year interval and to see the maximum and minimum points, graph F in a window 0 to 25. This would be 2 years. And the y-axis would be from -45 to +45. So this is what it would look like on your calculator. And we know that this is, since this is a graph of the weather of a year, we know that its period is 12, because that's how many months are in a year. Okay? So we know that our B component, our B multiplier, is pi over 6. According to the model, what is the average temperature during the month of May? Well, May is the 5th month of the year, so the average temperature during May is simply plugging in 5 for x, and we get this value if we plug this into our calculator. So the average temperature during May is 12.18 degrees centigrade. And I'm not sure how that corresponds. I think that's about, it's pretty chilly. I think it's in the 40s or 50s. Okay. And here we can easily see this in a table function. If we plug in our original function into y equals on our calculator, then we can go to the table function and look at what the y value is when the x value is 5, or you can use the trace function and trace along your graph until you get to x equals 5. Okay. What would be the approximation for the average yearly temperature at Mould Bay? Well, since the sine function is periodic and it's centered here on 0, that means that the values above and below the horizontal line are exactly the same. So the horizontal line, which is 0, is going to be our average yearly temperature.